I'm not clear, I'm doing this, it's okay to remind me that we need to start the quizzes. So the other thing is that you got your grades for homework. So let me just say a few things about those. So so they're just finished grading this morning. So it seems the grades were so like as a whole as a class were probably slightly lower than I was expecting. And so I think part of this has to do with as I create questions, sometimes they're a little bit harder than I intended, a little bit easier. And there were two questions that I think were both a little bit harder than I expected. And so I hope the rest of the semester the grades will be higher. You know, hopefully you're all studying and learning a lot, but just they won't be kind of some subtly tricky aspects of multiple questions that will trip up as so quite as many people. I spot checked a few of the homeworks before I unmuted so all of the grades, and there were comments on some of the PDFs that were turned in, but there weren't comments. There may not have been comments on all of them I'm hearing. So I probably may have erred on the side of releasing them early so you can see them before the quiz, but we'll try and give a little bit more comments in the future on the grading of the homework. If there's something you think was graded incorrectly, and this happens with the class of this size and grading up a bunch of homeworks, the right procedure is spelled out in the syllabus. You have either, I forget, a week or if it's 10 days to send me an email. And it's best if you see the TA who graded as well and say, I think there was a mistake. Here's how I think this should have been graded. This happened, so feel free to email. But you should do it within the next, so like a week or so. Yeah.
Will you be like posting answers or anything so that if we don't have comments, we have some way to tell how it was graded?
Yeah, so I'm not planning to post actual answers. I was planning to go through a couple of the questions at the start of the lecture right now. Okay, I think questions 1 and 4, most people did absolutely fine on. If you're not sure what you got wrong after I go through this today, so you should email first so the TA will lock and you can provide the answers. I don't know if you prefer email or comments on Canvas. I know if there are comments on Canvas, there are so many of them, I don't notice all of them, and email for me is better, but
yeah, email should be good.
Yeah, so I think email, he's sure to see an email. If you just leave a comment on Canvas, so he might not see it. Okay, so let me start by going through questions 2 and 3. I might not go all the way through 2, but I'll at least go through question 2. All right, so this was about a student who had to turn in an assignment, and and there's the time they would turn it in, and then there was up to some time. This is the area where it's late. That's up to 5, 4, make this a little bit, 3, 2. This is the amount of time late. It could also be -1, -2, up to -5. And so and for every minute that's late, it's so $1 fine for each minute late. Okay, and so the other thing we learned is that it's going to take them some time to complete the assignment, and that's a uniform. And this time is going to round down. So for instance, I said if it's 2.6. This rounds down to 2. So this is $2 late in here. Okay, so there's also a uniform distribution on the time to complete the paperwork between 4 and 8 minutes. Okay, there was some confusion on, well, it's uniform in between here, but the difference between these is 4 minutes. So the PDF, if I integrate over a length 4, the height is going to be 1/4. And it doesn't matter, if it's uniform, I'm never going to have, with probability 0, it's going to be exactly 8 or exactly 4. It's the difference between these that corresponds to this 1/4. All right, so the first case was if I start immediately, then I'm going to be done with a uniform distribution. I can shift this from -5 to -1 to 3, and it's a uniform over here. And if I fall in this bin here, which happens 1/4 of the time, I don't really need to do an integral here. Then the find is 0. The find is also 0 in this bin because it rounds down. So the find is also 0 here. This has a fine of $1, and this has a fine of $2. So the total, the expected value of some random variable of the fine is going to be equal to 0 times 1/4 plus 0 times 1/4 plus $1 times 1/4 plus $2 times 1/4, and this is going to be 0.7. So expected fine of 75 cents. Okay. Then the other question was, well, let's say I can't start at immediately, so I have to wait until -3 minutes to start. Okay. And so what this does is it shifts this uniform distribution to be here. Okay. And so now it's uniform over 1 to 5 minutes late. And so there was what a number of people tried to do is apply the linearity of expectation. Okay? And so the thing is, the expected time that things were completed shifted. So I have two random variables. I've got a random variable of time, of t, which is time, and also a random variable of the fine. Okay, and there's some function that gives me the random variable of the fine. And so if I know the random variable of time increases by 2, well then if I have linear of expectation, I could write that the f of t plus 2, the hope here is that this would be equal to f of the expected value of f of the expected value of the time plus 2. But this is not true. I can't do this because the f function is not linear. Okay, there are two ways it's not linear. One is it's actually the step function because of the rounding down. It turns out that actually wouldn't have mattered so much. But the issue is it essentially looks like this. So it's linear here and it's linear here, but it's got two parts. It's 0 before here and it increases afterwards. So I can't quite do something like this. Instead, I have to rework it from scratch. Okay, and so if it falls in this zone, this is going to give me a fine of 1, this a fine of 2, this a fine of 3, and this a fine of 4. And so the expected value of the fine is going to be 1 plus 1 times 1/4 2 times 1/4 plus 3 times 1/4 plus 4 times 1/4, and this is going to be equal to 10 over 4. Is that right? So $2.5. Okay. So it's a little tricky. You have continuous and discrete random variables and no linear of expectation, but you might have thought you could have done that. So there were some subtleties in this question, and I think this got more trick people up a little more than expected. Yeah.
For part one, what's wrong with the argument saying we've got a uniform distribution 4 to 8, the mean is 6, so we can expect to be 6 minutes late. And so we can expect to take 6 minutes to complete it, so we can expect to be 1 minute late.
So again, what you're kind of doing is this works if this find function is linear, then this would work. You're finding the expected value of time. So what you're trying to do is say the expected value of f of t is equal to the find function of the expected value of t. Right? There's some function that takes whatever time you're late and applies a find to that. Right? But I need to compute that inside the expected value. I can't pass this outside because it's not a linear function. Right? So it's a kind of it's definitely a tricky concept. But this only works if the f function is linear and it's not linear. And if you work through the case, I mean, you can see that that'll give you the wrong answer. Yeah.
So if it wasn't the case that we have to round down, would we just take the integral over that whole thing and it would just be the area under it, rather than?
Yeah, you could do the integral of the find function instead, and said it was measured in effectively cents or subcents, and what would happen is it would effectively shift this by half, right? Because I'm rounding down about half a minute. I get rounded down on average.
Oh. Okay.
So it's going to change the function a little bit because the rounding down actually reduces the find some amount, but it's still nonlinear. This nonlinearity occurs here instead of here, effectively. But instead, it's actually this step function where it's flat. It actually looks like that. This is what the find function is doing. Yeah. If there's ever a problem like this, I highly recommend trying to draw a picture in time, and just if you kind of just work through the cases, you're going to understand it much better. So let me quickly say something about question 3. So question 3. You had these 10 measurements, which were supposed to be IID. It was like 1.72, 1.89. Up here, you have a prior on the true volume, which I believe was 2.0 minus the true volume squared, and the standard deviation on the prior was maybe 0.1. Okay, so it was so this is the prior, and then I asked you to write down and that the true volume, the V I said had to be rounded. And so it had to be rounded to 1 decimal point. This was not to try and make the problem harder. This meant you could just try a finite number of these instead of having to derive the optimal value. So you could just plug these in. But what's left to do is to kind of write down the likelihood and then combine it with the prior function. here in order to get a posterior distribution, and then plug in these values. And so the likelihood is going to be the product of these 10 measurements, and each of them was going to look like, say, this is x1, or let's say lowercase v1 here minus v so it's going to be the product of these, right? So you would need to actually write, a very short program that takes this product, and so then the posterior is going to be proportional to the likelihood times the prior. If you took the negative log of this, then this turns into a weighted sum. And you can take the weighted sum over all values v and plug in these and see whichever is the minimum for the negative log posterior or the maximum for the product if you don't take the minus. Okay, and there was some confusion in the notation of what was the likelihood, what was the prior, what was the data, how to plug those things in, I think was what the main confusion was. But this was basically how to set this problem. Yeah.
So I think kind of answered a question similar to this when this came up, but the reason that we can multiply all of the likelihoods together is because we're assuming that they're all dependent?
Correct. Yeah.
For this likelihood function, what does this B sub I represent? What does capital B represent?
Yeah, so the model, the mean of the model is one of these things, right? This is what I'm trying to guess is the most likely, the highest probability, the highest posterior model, right? Is from this set, uppercase B, and these are the data points. Okay, and I think one thing that ends up being confusing is I wrote the prior as a general PDF, and I used the general notation for a PDF, which was this function I labeled as f, and the variable here is an x, which is the general notation for a PDF. Unfortunately, I also said the prior is usually f, and the likely is usually f, and the prior is pi, and I think that caused some confusion as well, is my guess.
If we encounter like a math problem like this in an exam, would you expect us to go through the, arithmetic at the end, or just set up?
Oh, on the quiz or the final exam, I will not ask you to simplify anything. I'm asking you to write something down following some formulas which you should know, but I won't ask you to do any calculations or simplify. It's sometimes useful. I'll try and set stuff up so numbers are easy, and you can simplify them just so you can see, does this number make sense? So I'd always suggest trying to do that, but circle your non-simplified answer. And then if you mess up after you simplify, you won't get points taken off.
So you said B is the average, like the expected value from here?
So I want to find which of these values to label the measurement as being the highest posterior estimate. Right, this is uppercase V. Right, say all these measurements are lowercase v as kind of independent measurements I took, which I assumed were from a normal distribution with standard deviation 0.2. So then it goes into this formula here as the likelihood. Yeah.
So the answer for this one, we would take the negative log of the likelihood and prior, so that we can do that summation and add them together, and we would get one number at the end of that.
Well, you get one formula as a function of uppercase V, right? So you're going to get the posterior is going to give you a PDF, which is going to be a function of uppercase V given the set V1, V2. So this is going to be a function of uppercase V. All of these VI values I know. I'm going to plug these guys into here in this product. This only depends on uppercase V. This will only depend on uppercase V. This will be a function of uppercase V. I'm going to try all of these values and return the one which has the returns the largest one for the posterior, or the smallest one for the negative log posterior.
Could you alternatively differentiate and then just find Z which is closest?
Yeah, you could also do this weighted average technique I mentioned in class, or solve it with doing differentiation, but there's this weighted average technique. And that will also give you a continuous value, not necessarily one of these, and rounding should work. You'll know you'll be one of the two closest ones. You know this function is going to be convex, so it'll have to be one of the ones nearby, but you're not totally sure which one it will be. It's probably fairly symmetric, and it's probably going to be the closest one. But it's not guaranteed to be correct in all situations you would do this.
Well, if we were to do this with the weighted average, what would the weights be?
Yeah, so the weights would depend. Once I did the negative log of these functions, all of these are going to have a weight that's going to be, these are going to be divided by 2 times 0.2 squared, right? Because these will be divided by a smaller number than these 2 times 0.1 squared, right? So these will have a lower weight than this. This will end up having 4 times, the prior will have 4 times the weight of 1 data point, but it'll have 10 data points. So I could basically put 4 copies of the prior in, and all the data points and do a regular average, or I can do the weighted average with weight of 4 here and weight of 1 here, or I can scale them to something else. It doesn't, scaling across all the weights doesn't change too much. So it'll be something like 0.08 here, and 0. For each of these, and 0.02 for each of these. As 1, or 1 over that value. Yeah, 1 over 0.02 here, 1 over 0.08 for each of these.
So the context for those numbers is then the first part of the equation is weighted higher than the second part, and so our prior is. So what exactly do those numbers mean?
So the ratio of the standard deviation, I square that. And so if the prior is half the small standard deviation, then it's 4 times as big, weighted 4 times as much as 1 data point. This is in the negative log posterior.
Okay. And so the prior then is when you're talking about maximizing, P of B given the data. It contributes, the first part of the equation contributes more than the second part of the equation.
Well, so overall, this one will actually, the likelihood will actually count more because there are 10 data points. And this one will count effectively as 4 data points put together.
Okay.
So this one overall will count more, but there are 10 pieces. Each one of these pieces will count less than this one big piece here. And that just depends on the weight of how I set the problem up. But I could have changed those and it could be different. All right, so hopefully that answers it. I would, for your own sakes, I would go back and look at your homework and try and, if you didn't get all the points, try and figure out what you would have done to better. That's the right way to learn this material. Ultimately, what I would like you to do is to learn the material. And still like a lot of you did good at these questions, but just a higher percentage of you did worse than I would have expected, I think, just because they were a little bit more challenging than I had intended for them to be. Yeah. Okay. So, and this is, we took an extra 20 minutes at the beginning to do this, but I think you guys have learned more out of it. I'm fine doing that at any class. If you're like, look, I didn't understand something from the last lecture, feel free to ask me. There are some slack days built into the schedule a little bit later on, so I'm not worried about getting through everything we have to do. I kind of rushed it a little bit at the beginning because I think for many of you, the probability is a review, and I'd like to get into the kind of the actual data analysis techniques before we're like halfway through the semester. So, okay, so let's for the next 20, 25 minutes or so start the linear algebra part of the class, and kind of all of you hopefully have seen some linear algebra before, so I expect this to be a review. I'll plan to go fast. My plan is to give you kind of a data analysis point of view of what linear algebra is good for and how to think about these. And I think about everything very geometrically. I'll try and aid that view onto you. Hopefully it's useful. Okay, so from our point of view, linear algebra means talking about vectors, and so and some matrices. And the idea is that for the first 3 or 4 weeks of class, we talked mainly about effectively one-dimensional data. Everything was a scalar value. But when we're dealing with actual data analysis, the right way to think of these things as a single data point is often going to be a vector, and a data set is going to be a matrix. It's often going to be a convenient way to represent it. And what this will allow us to do is to take what we understand well in one dimension and just simply write it down, and a lot of things will generalize naturally to high dimensions. This course is mainly about the things that do generalize easily to high dimensions. There are more advanced techniques when things start to break down, but we'll see that in a lot of cases, you can just replace your one-dimensional intuition with higher dimensional intuition, and using linear algebra as the language to speak this, and you'll be able to deal with high dimensional data. Okay. Okay. So a vector V is going to be I'm going to write it like this. So this is going to be a d-dimensional vector. It's going to consist of d values, v1, v2, up to vd. It's written in these parentheses. That means it's the order of the matters. We'll talk also about sets if we haven't already. And then it has some curly brackets here. That means the order does not matter. In this case, everything is like has a specific meaning. The value of v1 plays a different role than the value of v2, and I know they're exactly d things I'm keeping track of. Okay, and so from a linear algebra perspective, I will probably write this as a column vector, v1, v2, up to vd, and I'll think of stacking these on top of each other in kind of this block, and then I'll write these square brackets around it to kind of represent as a vector, and later a matrix will have a grid of these things inside square brackets. Okay. You may also get a row vector instead. And then I will write it like this. Okay, so now I've written the same elements, but in a row instead of in a column. Okay, so from a computer scientist perspective, these really should not matter very much. They're both stored internally as so you'd store these both as like an array. You know exactly how long it is. I know it has d things. I allocate d units of memory, and I store them consecutively in memory. Whether it's a column or a row should not really matter so much. Okay, in other classes, this may be stressed much more. And here I'm going to try and unstress this, because I think it generally is, you know, in some cases it's important to kind of keep track of this for notational purposes, but I think it adds sometimes more confusion than it actually helps. So try not to worry too much about whether it's a column or it's a row vector. It's an array, okay? It's a d-dimensional array that you can store. Okay, and okay, so these are mainly interesting when these are so real values. And so this notation it's in the space. This is like in LaTeX is /in is what this thing is, and it's in the reals, the d-dimensional reals. Okay, so that means a single element, an object v here, is a collection of d real values. These are continuous values. In a computer, they're you know, they could be doubles, or they, you know, you can store them in different ways. We're not going to worry so much about the like the differences in precision. We'll talk about this later in the semester. In other linear algebra classes, this may have been a really big deal, the precision going on here. In this class, it's not going to matter so much, usually. Okay. Okay? And then the way I like to think about a vector is as a point. Okay? So this is going to be that example of R2. So this is a two-dimensional space. And a vector, my first example here, let's say this is going to be the vector A1 is going to be a point that's negative 0.5, 1. Okay, and that refers to that the first coordinate, this distance here, is 0.5, and from the origin it goes in the negative direction, and the second coordinate maps to here, and this is going some distance 1.0 in this direction. Okay, so this vector is a point. Okay, is a point right here. And the reason it's called, it might be called a vector, is because you can draw a vector from the origin that points up to, that kind of goes from the origin up to here. Okay, and so in some places in, like in physics, they say it's very important to distinguish between a point and the vector representation. Again, I'm going to say I don't think these are so different. Sometimes we'll use the same kind of piece of memory, which stores an array, to sometimes represent the point here, actually the physical location, and sometimes the vector from the origin, or a vector from someplace else, as we'll see. Right? So I would like you not to try and worry about, is it a vector or is it a point? It's both. Okay? And then, once you have this, then a matrix A, so let's write this as A, then is going to have some set of, it's going to be written like this, with entries A1, 1, A2, 1, A3, 1, up to A, this is A1, 2, this is A, 1D, up to A, ND, and D, and so this will be a matrix that's in the reals of n times D. So this will be an n by D matrix. That's going to mean it's going to have D columns, and it's going to have n rows here. Okay, so this is going to be a row, and so this will be a column, okay? And so we'll think of a row as a data point AI, which is then going to be of a vector AI, B, and this is in RD, right? So this row here, the ith row, is going to be a vector AI. And sometimes I'll change this notation with upper and lowercase. I'll try and generally have the rows correspond to a single data point in a d-dimensional space, and there might be n data points. Okay, so think of an n by d matrix as having n rows and d columns. That's n data points, each in a d-dimensional space. Okay, so as an example, here I'm going to have some other data points here. Let's say this is going to be this can be A2, which is maybe going to be 1.0, 1.5, and this might be A3, which is going to be what does this feel like? 0.75 minus 1.0 as another point here. Now I have 3 data points altogether. This forms a matrix. This would be this matrix A, which is going to have, so how many rows and how many columns? That's what I was saying.
3 rows.
Yeah, so 3 rows. This is A1, so it would be 0.5, 1.0. A2 is going to be 1.0, 1.5, and A3 would be 0.75 minus 1.0. This is a matrix. It's got 3 rows for 3 data points and 2 columns in 2 dimensions. Okay, so I can think of a point set or 3 data points as forming a matrix here, and then later on in class we'll look at, sometimes we'll directly analyze this as a matrix. We'll use lots of matrix operations to linear algebraic operations to analyze. Sometimes we'll think of them as point sets. Sometimes we'll think of them as matrices full of data. Okay, and then I can do a transpose. So then an important operation is called the transpose. And so that is basically an A transpose now. So if A is in Rn times B, then A transpose will be in R of D times N. So basically the columns and the rows kind of switch roles. And so in the case over here, in the example, now A transpose is going to be minus 0.5, 1.0, 0.75, 1.0, 1.5, minus 1.0. Okay, so after I've done I can do a transpose of a vector as well, and I did the kind of example here from a row to column vector. They're still stored the same. Typically, an internal representation of a matrix will change whether you do A or A transpose. It may start as a long array, one row after another or one column after another, and it usually chooses one representation internally. So it may slightly change the representation, but it's really the same information here. Thinking of this as data points, this is kind of a strange fit, but we'll need this for some of the linear algebraic operations we do inside the algorithms. Yeah.
How does the notation A's in reals to the n times d correspond to like dimensionality or like geometrically? Like, what does that mean?
Yeah, so I think of this, and I have other colleagues who work in the same domain as I do, and they switch these around, right? But I think of this as endpoints in d dimensions. Now really it's n times d reals. So I've talked to other people who said really this is going to be an n times d dimensional vector of reals is equivalent in some ways. What will really matter is whether you put what kind of distance you put on top of this. And typically there are distances specified for matrices, and those will make more sense than to keep the structure of them being n rows and d columns. But sometimes you just unroll it into a single vector, and then it doesn't matter so much. So it's a little confusing, but I think of it as n data points in d dimensions as opposed to one n times d dimensional space, right? Instead of being a 6-dimensional vector here, I think of it as 3 points, each of them in 2 dimensions. That's why I think it was the most natural. And that retains the structure that is meant to be there in the matrix. But some cases, like a lot of computer vision, it unrolls it into a vector, and then early on they did this a lot. Now in say convolutional neural nets, they need to keep this neighborhood structure in some way inside the image. And so you can think of it all these different ways, and sometimes different representations are useful. Okay, but generally I think that's the easiest. Okay. Okay, and so now, for instance, vector A1 is a column vector instead of a row vector. Okay, so next thing I want to do, and then we'll stop, I want to do addition and multiplication again. And I'll just do addition of these quantities. So if I have two vectors, let's call them P and Q in RD, right? So then P plus Q is going to be a vector of P1 plus Q1, comma, P2 plus Q2, comma, up to PD plus QD. Okay? And so it's basically entry-wise addition when you're doing addition. What's important is that I can only, if the same dimension. I can't add together vectors in different dimensional space. It just is, it's not defined. If you think of them as points in a d-dimensional space, I can't, they don't live in the same kind of dimensionality. It's like trying to add right, so you can't add the kind of the units don't line up, sort of thinking of that. So you can only do this if they have the same dimensionality. And because of this, it's basically just adding up individual terms. With matrices, it's just a generalization of a vector. Say I have A, B, they're both in R n times D. Then I basically, this sum is going to be equal to this large entry here, where the first one is A11 plus B11. Then A12 plus B12, and so on. Okay, so again, it's entry-wise addition, and because of that, the dimensions have to line up. Okay, so if I set, say, n equals to 1, then these are vectors, and so vectors is just a special case of this. And I can, so A plus B is equal to B plus A, and A plus B plus C is equal to C plus A plus B. I can switch the order of these things because it inherits all the properties of addition. It's just entry of this. Okay. Okay, so we got a little delayed, so I think I will stop, and we'll start with multiplication so Wednesday, and we'll talk about things like the dot product, which is a very Very cool operation. And norms and stuff like that. Okay, so so now I'm going to hand out the quiz. Just a refresher on the rules for the quiz. You get one kind of note sheet with, you can write anything or print anything you want on one side of it, but not the other.